Hi everyone, my name is Gonzalo Parra and I am very happy to be here today to present our work about energetic local frustration and protein dynamics. So in order to understand local frustration, we have to see that proteins are not optimized to fold, but to function. So according to the energy landscapes theory, when proteins fold, they minimize their internal energy according to getting more and more similar to the native state. However, in the native state of proteins, not all interactions are energetically minimized, but some stay in conflict, and this has been true over evolutionary scales. So if we think of the native state of proteins as being a set of conformers that exist in a dynamic equilibrium, we can think that these highly frustrated interactions or interactions that are in energetic conflict, they are useful so the protein can transition among these different conformers. So over the years, Ferreiro and co-workers have developed the concept of frustration. They developed an algorithm to localize frustration in protein structures. So if in a protein structure we can define which residues are in contact with each other, we can take a given interaction between residues I and J, and by taking an energy function, we can calculate its native energy. And then we can perturb this native interaction by creating decoys, and we can calculate the energetic distribution for these decoys, and we can compare the native energy to this distribution. So if most of the distribution has more minimum energy than the native interaction, then we can say that this interaction is not optimized and is highly frustrated. If the other thing happens, that most of the distribution has a worse energy than the native interaction, then we can say that this interaction is optimized and is minimally frustrated. Otherwise, it's neutral. According to how we construct these decoys, we are going to talk about different types of frustration indexes. If we modify the identity of the residues only, we are going to talk about the mutational frustration index. If we modify the identity but also the distance between these two residues, we are going to talk about the configurational index. And if we modify only the identity of one residue and we check how the energy changes for this residue and the interactions that it establishes with all the other residues in its environment, we are going to talk about the single residue frustration index. So over the years, Ferreiro and co-workers, they have seen how frustration is distributed in different types of sets of proteins. So they checked for a representative set of proteins in the PDB that are monomeric, that up to 10% of the interactions are highly frustrated, and around 40% of these interactions are minimally frustrated. The rest are neutral. These interactions are not randomly distributed but localized in specific regions. For example, the minimally frustrated interactions are mostly located in the hydrophobic core of proteins, whereas the highly frustrated interactions are mostly located in the surface of proteins. They are enriched in regions that are known to bind other proteins, and also in regions of the proteins that are linked to allosterism. Over the years, a lot of people have used this algorithm because since 2012, this is available to the community as a web server. We have updated it in the middle up to now, and we have made it faster, and also we have included some terms in the energy function that are able to see how electrostatic affects frustration. There are more than 230 works that have cited this server. We have gotten many requests over the years to install it locally. This was not easy. And so because of that, we recently have published a new version that is an R package that allows people to calculate local frustration in a programmatically way very easily in their computers. With just a few lines of code, we can recreate all the plots that are available in the server, but also there are some new modules that we have included. For example, we have created a new module that it's useful to analyze how local frustration changes across molecular dynamic trajectories. And the cases of study we're going to show, it's about IKB alpha, that it is an inhibitor of NF-kappa B. We have performed folding simulations of ISMB alpha using a Go model within the ISMB suite, and we have calculated the energy for all the conformations across the trajectory, and we have also projected this energy into some other coordinates like the radius of duration and Q, which is a measure of how similar the different conformers are to the native state. So when we observe the landscape of this protein, we can see that there is an unfolded state, there is a folded state, these are representative structures, and there is also an intermediate of folding here and an expanded conformation here and here. So we can analyze this trajectory further with frustatometer. We can see how frustration changes for the different residues across simulation time, as well as for the interactions across the contact map. And also we can see how frustration changes for specific residues as a function of simulation time. And by doing this and by using some other modules that are useful for detecting clusters of residues that have similar behaviors across the dynamic, we can, for example, take all the profiles as a function of time for all the residues in the structure. We can fit some models to the distribution of points, and we can calculate which are the maximum and minimum values for this model in frustration over time. And by comparing this to the mean frustration of this residue over the simulation, we can detect by taking some thresholds which of the residues are variable across the different frames in the dynamics. We can perform over these residues a principal component analysis, and over the resulting principal components we can calculate some correlation values, and we can see which residues are similar to each other in terms of frustration in this that are projected into this principal component space, and we can create a graph, of course, and then we can cluster it to just get the clusters of residues that are similar in their frustration behavior over time. And for example, this is a residue from cluster 1 that over time becomes minimally frustrated, and this is another example of cluster 2 that over time becomes highly frustrated. For ISMB alpha, we detected some different clusters, and we got some very nice explanations or analysis we can make over them. So for example, there's a set of clusters here that are having some specific behavior. They all change their frustration in the more or less same moment in time. And this moment in time corresponds to the moment when the protein overcomes the energy barrier here to start to populate the intermediate state. These interactions are important to establish interactions within and inter the helices in this region here, and these interactions here are important for the interface between ISMB alpha and NF-kappa-B, which is not present here in the simulation. Something similar happens to these clusters here, with the difference that these clusters change their behavior in a later moment in time, which is corresponding to the moment when the protein overcomes this barrier here, then to start to populate the expanded state and finally becomes fully folded. So this is a very nice example on how we can use frustration to try to give further insights about how are the different folding mechanisms in proteins. So for the second type of my talk, I'm going to talk about our new analysis about frustration across NMR structures, which are a proxy to kind of try to study and understand protein flexibility. This is unpublished work, mainly led by Attilio Rauch and in collaboration with Leandro Radusky and Alexander Monzon. So we took all the NMR structures in the PDB, and from this we took the ones that we are able to map to UniProt IDs. We kept the structures, the entries that have more than 10 models and are longer than 50 residues. And then we reduced sequence similarity to 40%. So we got a final set of almost 3,000 clusters. For every cluster, we took a representative structure, which is the one that has the number of models closest to the median number of models in the cluster. So for all of these structures, we are going to show some analysis now. So we created new modules to analyze NMR structures. For example, for these two examples here, we can calculate how frustration is distributed for the different residues across models. We can see that there is variation for the different residues. Some residues vary little, some others vary more. And here we can create this kind of movies for showing how conformational changes occur across models, and we can map for every model the frustration, in this case configurational frustration in the contacts, and in the backbone we are coloring according to which is the difference in this, like which is the range for every residue in terms of the difference between the minimum point and the maximum point here. So we can observe that those regions that are more variable in their conformationally speaking, they have more red interactions, and also they are more red in the backbone. So this we want to study a bit further. So we took for every NMR structure, we took the median single residue value across models. So, and we created the distributions for this for all residues in all our data sets, and we classified them according to their amino acid type, identity. So we observe here already some interesting stuff. So hydrophobic residues and cysteine, for example, phenylalanine, they are usually most of the time minimally frustrated when we talk about the medians of the distribution. Then the others are all in the range of neutral frustration, which from where tyrosine is the one that is closest to the highly frustrated interaction. So we further separated this data set into different secondary structure elements. We mapped the different residues into being part of alpha helices or beta sheets or unstructured secondary structures according to the SSP. And here we can see that the distribution doesn't change too much, but we can see some already differences. For example, the unstructured residues, usually they have higher frustration than their structured counterparts. And for example, if we further separate this data set into exposed and non-exposed, we can first see that these residues here, the hydrophobics and the cysteine, they stay minimally frustrated for both the exposed and the non-exposed data set, but there are some others that change. For example, the phenylalanine and the methionine, they are minimally frustrated when they are non-exposed, but then they are neutral when they are exposed. For example, for the tryptophan and the tyrosine, this is also very interesting. They are neutral when they are non-exposed, and then they are very highly frustrated when they are exposed. Then we have a set of residues here that they don't change from classification, but they are more frustrated when they are non-exposed. So in many cases also we can observe that the residues that are in the structured part of the dataset, they are more frustrated than the ones that are in beta sheets or alpha helices. So we started to ask ourselves if there is any relationship between frustration and order and disorder. So if we go back to the movies which I showed before, and we compare now in the backbone, we are showing the IUPRED prediction as a color. We can see that the regions that are more mobile and more frustrated, they are also corresponding to the regions that are more disordered according to IUPRED. So we calculated, we classified all our residues as being non-disordered or disordered according to IUPRED, which is based on sequence, and according to MOBI, which is based on structured. And we see that distributions are pretty similar, with the difference that here the tryptophans and tyrosines according to MOBI are more frustrated, especially when they are mobile. We observed that, for example, in this part of the data set, for these amino acids, the disordered part is more frustrated than the ordered part. But for example, for these other residues, it's the other way around. The ordered part is more frustrated than the disordered part. And the maximum difference is observed for histidines here, where the disordered histidines are more minimally frustrated than the ones that are ordered. And when we check them manually, we observe that this is mostly corresponding to histidines that are located as clusters of histidines in exposed loops. So this is already kind of interesting. But this is all showing the differences in single residue frustration, which can be a little bit tricky, because if a residue has half of the distribution of contacts in the minimally frustrated classification and the other half in the highly frustrated classification, then the index is going to show an average, which is going to be neutral. So this can be masking some effects. So we can calculate now the mutational frustration that is assigned to contacts, and we can calculate the pair distribution function around different types of amino acids to see which is the enrichment of certain types of interactions around the different specific amino acid identities. So when we separate into ordered and disordered residues, we can observe already that for the orders, there are specific amino acids that are clearly minimally frustrated, and when we observe the disordered counterpart, they are completely different. They are highly frustrated. Some of them, they stay the same, minimally frustrated, but this is already showing that there are differences between ordered and disordered residues in terms of frustration. And mutational frustration index takes into account the amino acid identity. But if we take into account also the conformation and we calculate the configuration of frustration, we observe further things here. For example, the alanine and the methionine, they are not minimally frustrated anymore when they are ordered, but also the residues that were disordered before and minimally frustrated, now they are not minimally frustrated anymore. And so the whole data set is really highly frustrated when we take into consideration disorder and configuration frustration. So in order to finish, my conclusions are that we have developed a frustratometer, which is a very easy to use R package to calculate local frustration programmatically in big data sets and locally. Frustratometer now contains new modules for analyzing molecular dynamic trajectories and to find dynamic residues and that may help us to understand folding mechanisms in proteins in molecular simulations. We have developed also functions to better analyze NMR structures, and according to this preliminary analysis we have made, there is a correlation between amino acids identity and the frustration propensity. This is a confirmation of previous work, but also extended to a way bigger data set and also in the context of flexibility in NMR structures. There are differences in frustration between ordered and disordered amino acids, and very interestingly, not necessarily when there are amino acids that are more disordered, this will mean that they are more frustrated, because there are different examples where this is the other way around for many types of amino acids, and a very specific type is represented by the clusters of histidines that are present in loop regions. So to continue this work in the future, we want to see if can we create a frustration alphabet in terms of, for example, like when residues are classified into polar, non-polar, hydrophobic, non-hydrophobic. Can we link frustration to disorder or order or solvent exposure, and to create a kind of alphabet of classification of residues based on frustration? So this is what we're going to continue to do. So I thank my collaborators, specifically Attilo Rauch, who has been the leading force behind all this work, and of course all my collaborators, and of course all of you for listening, and I will be very happy to take questions now. Thank you very much for your attention.